All right, this is the sequel to the last lesson, the action-packed sequel, in which we will primarily use the ideas of integration by substitution to find definite integrals, as we see here. And in doing so, using the part 2 of the fundamental theorem of calculus. So here we have a definite integral, and I want to find the area under the curve between 0 and 1 of this 50th degree polynomial. All right. So to do this, though, really the majority of our work is finding the antiderivative, because I know that this will equal the antiderivative of this at 1 minus the antiderivative of that same thing at 0. So really most of my work is, okay, what's the antiderivative of 30x minus 1 to the power of 50? Well, again, I can see a composition of functions taking place here, so I know I can't just use the power rule in reverse right away, which means I probably want to use integration by substitution. And so let's start with assuming that 30x minus 1 is the inside function. So let u equal 30x minus 1. And therefore du would be 30 times dx. And then looking at my integral here, there's the dx. I don't have a 30, but as we saw, that's easy to take care of. I can put a 30 into here. I can say times 30, as long as I put divided by 30 over here. And now I can, and I'm not going to worry about the definite integral right now. I'm not going to worry about the bounds of 0 and 1 just yet. I want to really focus on my indefinite integral. So I have 1 over 30 times u to the power of 50 times du. Okay, use the power rule here, and I quickly get 1 over 30 times u to the power of 51 over 51, which is the same as 1 over 30 times 51, which is 1,530 times u to the power of 51, plus some constant, if I'm thinking about the indefinite integral. All right, so what I want to do now is I want to now, let's put my 30x minus 1 back in here. So I guess I'll write it as 1 over 1,530. Oh, that's a weird looking number. Let's try that again. Times 30x minus 1 to the power of 51 plus c. There, that's my antiderivative. Okay, but again, I want to evaluate this now from, 0 to 1. And so at this point, I can just deal with this whole part right here from 0 to 1. Or what I'd actually rather do is that constant value of 1 over 1,530. I'd rather just kind of keep that out. I mean, it's just a constant. So I'm actually going to deal with this. I'm going to leave this in the front and then use this. 30x minus 1 to the power of 51 from 1 to 0. That's what I'm going to evaluate here. Okay, and so now it's a little bit messy here, but it's pretty much done. And so in this case, I get 30 minus 1 to the power of 51. So 29 to the power of 51. I'll just write that down. Minus 30 times 0 minus 1 to the power of 51, which is just 1. Or actually, sorry, it's minus negative 1, so maybe I should do it in 2 steps. I get minus 30 times 0 minus 1 to the power of 51. So again, all of that right there is negative 1. Negative 1 to an odd number is still negative 1, so I'm subtracting negative 1, and so hence I said this is all plus 1. And I'm essentially done here. I could write it as, 29 to the power of 51 plus 1 over 1,530, but I don't really care about that. And again, I could go to my calculator. It's clearly going to be a very, very large number in scientific notation. Let's just leave it like this. So notice, I had a definite integral, and I had to, at some point, use this fundamental theorem of calculus right here. But really, most of my work was just finding the antiderivative. All right, let's look at this. Same idea. Most of my work will be finding the antiderivative, which means, again, I need to think about what was my inside and my outside function. I'm going to assume that minus x squared is my inside function, because I can see it's inside this exponential function. So I'm going to say let u equal minus x squared, which means du will be minus 2x times dx. And now looking here, if I look at that, I have the dx, I have the x, I don't have the negative 2. So again, I can create a negative 2 there as long as I divide by 1 over negative 2 here, or just multiply, I meant, by negative 1/2 in the front. So everything seen in blue kind of matches up. Everything seen in yellow, I can substitute. And so now I can think about my indefinite integral with a negative 1/2 in the front. And so I have just u, oh, not u, sorry, e to the power of u times du. That's quite nice, because the antiderivative of e to the power of u is e to the power of u. Now, that's my antiderivative, although I'll do a few things. I don't really need the constant, because again, I'm going to use the antiderivative, and that u, I want to change back to minus x squared. All right, and again, this is what I want to use the fundamental theorem of calculus part 2 for, with these two bounds of 0 and 1. And again, that negative 1/2, I'm just going to kind of leave outside of it because it's a constant. So I'll just go like this. And so I get e to the negative 1 squared is negative 1, minus e to the 0, well, minus 0 squared. That's quite nice. What do I have here? I have negative 1/2 times 1 over e minus 1. And the answer is great like this. That's it as well. You know, it's not hard for me to find a common denominator inside the brackets. And then put it all together as one expression, one fraction, I should say. And if you do that, you get e minus 1 over 2e. But again, everything, all of these are great. Although I kind of like the last one the best, but I don't really care. All right, let's look at this one. It's a definite integral involving a. And again, I'm integrating with respect to dx, so I know a is a constant. All right, so again, yeah, there's a lot of variables here. The only constant number that I know what it is that 0. Everything else is a variable in some extent, although again, I'm treating the a as a constant. And so first, let's assume that this is the inside function. And so that means du will be, now again, a is a constant, so the derivative of a squared is 0. So I just need to think about the derivative of minus x squared, which is minus 2x times du. And again, this is where I start to get a sense if I guessed correctly with my with my inside function. If I look here, I have a dx, I have an x, I just don't have a negative 2. Like we see, I can take care of that if I just put negative 1/2 in front of this whole thing, just like the last question. And again, if you want to, I can also write a little times negative 2 right here. And you can literally see how everything in blue connects back. And so I'm now going to rewrite this as just the indefinite integral with a negative 1/2 in the front. What do I have? I have just the square root of u du, or even better, u to the 1/2. I'll say even better because for integrating or differentiating, that's easier to deal with. All right, so using my power rule now, I have u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3, all plus some constant. And again, that constant in the end is not going to matter because the question was actually asking me to find a definite integral. But at this point, I also might as well take advantage of the fact that I have 1/2 times 2/3, which is just 1/3, or negative 1/3 in this case. So I'll write that constant in the front. Negative 1/3 times u to the 3/2. Or actually, in this case, let me just take that u right now and change it to a squared minus x squared. All right, so now it's a matter of just substitution. And so leave the negative 1/3 in the front. Substitute first x with a. And so what I get there is a squared minus a squared, which is 0 to the, I don't care anymore, it's 0. Minus, now substituting x with 0. And so I get a squared minus 0, which is a squared to the power of 3 over 2. Well, power of 2, 3 over 2, that's just a power of 3. And so this is now going to start simplifying really quite nicely. I have just minus a cubed. And then looking at that, I have negative 1/3 times negative a cubed. That's the same as just a cubed over 3. There we go. Remember, that's not an antiderivative. And my a looks like a 9 there. That is not an antiderivative. That is, let me fix that up. That is the definite integral. That is the area under this curve from 0 to a. And again, depending on what a is, well, you can see how that's going to affect the overall area. All right, so second last question. Very, very similar. I have a visual here that, you know, I could use it to different degrees. But I have a graph here, and the graph of the curve is y equals the sine of 2x minus the cos of x. And my question is to show, in any way I want, show that this area here and this area here are exactly the same. Now one's negative, one's positive, but I'm saying that they are the exact same area in terms of their absolute value. How can I prove that? Well, one option, which I'm not going to do, is to find the integral from 0 to pi over 6 of this function. And then separately find the integral from pi over 6 to pi over 2 of the same function. And I should get eventually two numbers that are identical, except one's negative and one's positive. And that's a great idea. It's just more work than it has to be, but it is a great idea. So what's a bit less work? Well, if these two regions really have the exact same area, and one is negative and one is positive, then I know that altogether the two of them, the area together must equal 0, which means I know the integral from 0 to pi over 2 must equal 0. And so if I can show that the integral of this function, sine 2x minus cos x from 0 to pi over 2 equals 0, then I've proven these two must be the same. So I like that a little better. So I'm going to set it up like that. I'm going to say the integral from 0 to pi over 2 of the sine of 2x minus cos of x dx. I know this equals 0. Now with that said, I know that's true, but now my job is to define that it equals 0. Essentially, I know what the answer should be. Now I got to find it. So I'll just leave that for a moment. But assuming I eventually see that this equals 0, then I've proven this. Those two areas must be the same. Okay, so again, I want to integrate this. Now I will say, if I look at these as two separate terms, well, they are. The second term, cos x, that's really easy to deal with. The antiderivative of cos x is sine x. So it's really just the sine 2x that's a bit trickier. So I'm actually going to break this up into two separate integrals. I'm going to break it up as the integral from 0 to pi over 2 of just the sine of 2x dx minus the integral of 0 to pi over 2 of cos x dx. And I can just see, again, what the antiderivative of cos x is. And so really most of my work is focusing on the sine 2x part. And so that's what I want to focus on. So for that, I want to let u equal 2x, and therefore du will equal 2 times dx. And if I look again at just this part here, oh, I got too much blue highlighting going on. Let me go to a lovely sort of pink. There we go. So if I look here, if I look at the first integral, I have a dx. I don't have a 2, but like we know, I can take care of that quickly, putting it there. Now I have a 2. More importantly, I just got to put a 1/2 in the front. There we go. And so I'm going to let u equal 2x. And so again, focusing on just that first integral, I'm going to focus on just the indefinite integral. I have 1/2 times the sine of u du. And so I can see that that now equals 1/2 minus cos u plus some constant, or minus 1/2 the cos of 2x plus some constant. But really, it's this part that I care about. And so what you see underlined in orange is the antiderivative of this part. And again, I've known for some time what the antiderivative of the cos x part is. So now let's put all this together. So I'm going to really take this step here, and I'm now going to think of it like this, as negative 1/2 the cosine of 2x evaluated from those bounds, which were pi over 2 to 0, minus the antiderivative of cos x, which again is just the sine of x, again evaluated from those same two bounds. And so hopefully you can see now how this step up here has brought me to this step right here. All right, so now let me just focus on this. Ooh, don't have much space left. The good thing is I've done all the main work. And so right here, I get minus 1/2. The cos x of 2 times pi over 2 is the same as the cos of pi, and the cos of pi is negative 1, minus the cos of 2 times 0, which is the cos of 0, which is 1. There's that part. And then I have another one to evaluate here. The sine of pi over 2 is 1, minus the sine of 0 is 0. That's come together quite nicely. And clean things up, eventually you get exactly 0. You get 1 minus 1. And again, that's what I wanted to get, right? In the end, I saw this whole integral equaled 0, and I said right from the start, if I could show that this whole integral equaled 0, then I have proven that these two must have the same areas. That said, though, if you were to find the area of each of these separately, off the top of my head, I don't know what the answer would be, but one would be negative, one would be positive, they'd be the exact same, and it would be more work. Not a ton more, but it would be more work. All right, here's the very last one. Again, evaluate this indefinite integral. For this one, it's extra tricky because of this, the fact that trigonometric functions are all kind of related to one another and can be simplified to one another. And you know, to integrate this, you probably need a hint. And so if we just say, for example, if we just say, you know, what's the inside function? Maybe we say the inside function is cos x. Well, then du would be minus sine x dx. But there's no sine here anywhere. So I'm kind of stuck. Although, I could have a sine there if I chose to use various identities to rewrite it. And so again, right now I can't do much, but let's think about some ways to rewrite it. And so one thing I would do is if I rewrote cos x cubed as cos squared x times the cos of x, then I have some options, because the cos squared x, using the Pythagorean identity, is 1 minus sine squared x. Why is that helpful? Because now at least I have sine and cosine. With that said, now let's try doing some substitution. Now let's say let u equal the sine of x. And why am I picking the sine of x? Because I know the derivative of sine x is cos x, which I see right there. That's why I'm choosing it. And so let's let u equal just sine x, and therefore du equals cos x, which I have there. And so if I put my integral notation back in, dx, my integral, I'm going to focus on the indefinite integral right now. Notice cos x dx, that's what I have down here. And so I can actually rewrite this quite nicely now, as again, still focusing on my indefinite integral, as 1 minus u squared times du. Well, I can integrate that. The antiderivative of 1 is u in this case, because I'm integrating with respect to u. Minus the antiderivative of u cubed is 1/3, sorry, the antiderivative of u squared is 1/3 u cubed plus some constant. And keep in mind, all those u's are actually sine x. And so now I can start to evaluate this integral, this definite integral. So I can find, the sine of x minus sine cubed of x over 3, because that's what u was again. And I'm integrating this from pi over 2 to 0, looking at my bounds up here. So from pi over 2 to 0, which are nice numbers, so which means I should be done quite shortly. And so now looking at this, starting with the sine of x, the sine of pi over 2 is 1, minus the sine of pi over 2 cubed is still 1. So over 3, that's the first part of the bound, minus was 0. The sine of 0 is 0, minus sine of 0 is 0, so cube it, divide by 3, you still got 0. And so lo and behold, this is just 2/3. And I'm done. Tough question, because, is how to get it set up. Which really, if I go back to this right here, that was my antiderivative. If I gave you just this sine x minus sine cubed x over 3 and asked you to differentiate it, you would get to something like this. But then, if you were to simplify it, that would bring you to here. And it's, when you're dealing with trigonometric functions, they're all interrelated. There's never one way of expressing a trigonometric function. And that's really what made this especially challenging. But now you finally don't have to hear me talk any longer.